Hey everybody, how you doing? We're getting there. We got 17 people so far. Got another. Woo-hoo. I'll give you a few more minutes just to make sure we get a decent number of people here. Well, I think we should go ahead and get started. So today we're working on chapter 32. Chapter 32 is on elementary particles. At least that's what it's called, but we go through elementary particles, fundamental particles. We even talk about things like supersymmetry and the standard model, electroweak forces, all the forces of nature, accelerators, how you can use accelerators to probe the interiors of nuclei and stuff like that. So there's a lot of stuff covered in here. The main thing I want you guys to be able to do for my class is be able to work sort of the problems that you see in the examples of the chapter, which are things like when they make a nuclear reaction, they will leave one of the items out on the product side or maybe even on the input side. And when they do, you have to use your conservation laws to figure out whether or not, or figure out exactly what thing has been left out. So you'll have to find out, whether it's a proton, a neutron, a helium nucleus, a hydrogen nucleus, or something like that, or if it's one of the crazy particles we learned, maybe it's a chi-0 particle or something like that. So it's not that hard. It just turns out there's more conservation laws than we know of so far. So we've already learned about conservation of energy, conservation of linear momentum, conservation of angular momentum. We've also learned about conservation of charge. And before we were talking about conservation of nucleon number, but in fact, what we're going to switch to is conservation of baryon number. Then we'll bring in the electron lepton number, and then the mu lepton number, and then the tau lepton number. Those will be conserved as well. We'll ultimately bring in Strange and stuff like that as well. So there's a quantum number called Strange too that was discovered. And some of these conservation principles won't be the normal conservation laws in that they are sometimes violated. So for instance, strangeness can be violated in the event of a weak force interaction as opposed to a strong force interaction. But in a strong force interaction, strangeness will be conserved. So little things like that. You can pretty much get it all from the reading. This is, though it's one of the most information dense chapters in the entire book, it's still pretty straightforward. The paragraphs that have, obviously a lot of words and stuff like that are more likely to need to be read 2 or 3 times before you can make sense of it. But I'm just going to sort of lightly skim it, work some of the problems similar to ones that your textbook uses and stuff like that. Anybody have any questions before we get started? I know I got one email. Someone suggested that the tests the midterm that I made open for everyone, they said that it needed a code. And since I just copied the existing midterm, I didn't think I added a code at all or a password or anything like that to access it at all. But if I did, it would have had to been the same one that we did for the midterm. So that I said that was 2319 capital S, then lowercase ULLY. So 2319 capital S ULLY should be the password for you to get there. Isaiah, are you here? Isaiah, I think, was the one that emailed me, and I think, yeah, he's here. Isaiah, did that password work for you? He might not have tried it yet, or his speaker might not be working either. So anyways, that should work. Remember, you only have to put in an answer. I mean, I think it'd be better for you to actually attempt to work it out instead of just making up answers, but you only have to put in an answer, and then it'll give you, once you put in all the answers and save it, actually you can even take a 0 on it if you want. It's not going to count as a grade anyways. But once you do that, you submit it, it'll give you the answers back, and then you'll know what to work to. The main thing is you got to do all those questions. Those of you who didn't score an A are eligible to do this. Those of you who scored an A, y'all did great. So no need to change that. Anyways, so do that and redo the entire test, not just the parts you missed. And remember, I said you have to have a photograph of the question followed by what the actual answer is, showing me all your work, and then question 2, all your answer, and then all your work, and so on and so forth. That's what I need turned in, again, preferably as a PDF. I'll have to put a location for y'all to do that. But anyways, if you do that, then I will take the higher of the two, the midterm or the, well, actually, correction. If you do better on the final, I will replace your final exam grade with that midterm grade. Or excuse me, I will replace your midterm grade with that final exam grade. I always do it so that it's basically the same thing as if I counted the whole final as 30% instead of counting the midterm as 15 and the final as 15. So the final is more comprehensive, and having shown me that you figured out how to do the midterm, then I feel justified in letting you substitute the final exam grade for the midterm grade. So anybody have any questions on that?
Yeah, so if we do the midterm review or redo, excuse me, it's only like what do we get from doing that? Like what are you doing with that score? I'm a little confused.
I won't. Well, that score should be 100. If you get 100, then I will allow your final exam score to replace the midterm score.
Okay, so if we do
So
that,
it doesn't really
have an option for that.
Exactly, and I'm probably going to do something like maybe add 10 points or something to the midterm, just to even in case you don't do necessarily better on the final than you do on the midterm. Okay. So I'll do something like that. Yeah, I think that's probably fair. That part of it, if anybody that did make an A, if they choose they want to get in on that 10-point action, then you're welcome to. I don't think you necessarily want to or need to, but you're welcome to, since I'm going to be giving points. So yeah, I'll probably give you 10 points if you do the redo of the test correctly. Show me all your work, and there's no a magic step occurred here or something. In other words, you don't leave out a bunch of steps that maybe is not completely obvious. Then I'll give you at least 10 points on the midterm, just in case you don't do better on the final. But I won't be able to do that till the end, because I got to see which one's better, the final or the midterm grade. And if the final is better than the midterm before the 10 points, then I'll submit the final for it. So does that make sense, everybody?
You said we have to take a picture of the question that we need to redo. How do we do that?
You can just do a screenshot. So if you're using a PC, you can look for snipping, SNIPPING. That's a snipping tool. If you're using a Mac, you can hit Control-Shift-3. Both of those will take a screenshot. Then you can crop out whatever you want. You can, just take the question part and then paste it in a Word document. That'd be fine. If you're using a phone, it's even easier. You know how to take a screenshot of your phone.
What Will we be
So
able to do that
make sure
before
you
starting the
go
test?
ahead. Would you be able to do that before starting the test?
Yeah. To
Oh,
take the,
it doesn't. No, not until you actually go in the test. And I think once you're actually have already taken the test and submitted your grade, when you go back to look at the test, the questions and the answers and now the correct answer will show.
okay.
So you can just take a picture of the whole thing and then you should write your work below it, paste that picture into a Word document, say, and then write your solution below it. I probably would avoid typing up that solution. That could waste a lot of time. What I would say do is maybe print out a page with that photograph on it and then neatly work the problem. It might even have to be your second pass. That's good enough for you to turn it in. Take a photograph of that and then paste that back in the Word document if you want. Or you can upload the photos. Generally, the photos take a lot more data, but if you can paste it into a Word document and then turn it into a PDF, that'd be best. I think with the concept questions, you won't be able to, you won't necessarily be able to write a whole lot about the explanation. You'll just, you should be able to explain it within 1 or 2 sentences. So you can probably fit all the concept questions on one page and 1 or 2 problems on a page. Anything else?
For the final next week, will we have class in the morning and then the final in the afternoon, or just the final?
I think what I'll do is I'll probably have the time for class so you can ask me any questions you might want, that sort of thing. But then I'll just let you break out and take your test at any time. Probably I'll have to set. Let me see. We're supposed to start class at 9:30. I'll set the final to start at, let's say, 10:30, and you have to start within 20 minutes of that, basically. So that way we won't run the whole class time, but I'll have at least an hour to work with you. If you need a little bit more, you'll have a little bit more time, but you'll need to start the test somewhere between 10:30 and, let's say, 10:50.
Okay, thank you.
And it'll be on Respondus with all that stuff. Okay, you're welcome.
Professor.
Hopefully, go ahead.
I have
Yes.
another question. I've said this before, but my classes start next week, and I haven't gotten like like when my Zoom sessions are supposed to be yet, and if they like run in
Gotcha.
like time to ours. I don't know if my other professors
Right.
will record their Zoom sessions because they'll want everyone to be there. So will I get like counted off if I miss
Right.
some class? Okay.
No, I don't. In fact, the only reason I take roll is because they want to know where when the last day you attended is in the event that you just disappeared or stopped attending or failed. So yeah, and I don't take any points off for it. So
Okay.
don't worry about that, JC. And you can always catch my videos. And actually, to be honest with you, today's lecture and Friday's lecture is really probably going to be the last real lectures. The rest of it's going to be probably question and answer sessions, knock off early, start your lab early. We only got 2 more labs to do too.
Okay.
So it should be a little easier for you. Okay.
Thank you.
All right. Well, let's get started on chapter 32. Does
I
somebody
had
else
the
have a question?
same question because my class starts Monday as well.
Uh-huh.
So I was just wondering the same
Right.
thing.
Yeah, no problem at all. Don't worry about missing. Like I said, I'm probably not going to cover any more new material after Friday because I can cover all of chapter 32 that matters today, and I can cover all of chapter 33 that matters Friday. So Monday, you don't even need to attend at 9:30 if you don't want to. I'll be here at 9:30. You'll do a lab after we're finished, and even when we're there at 9:30, it's just going to be a question and answer session. I'm probably not going to prepare anything to teach y'all more material. I'll just take question and answers when everybody's finished. We'll just jump right in the lab and do that. And then Wednesday, it'll be the same thing, but with no lab. So Wednesday, I'll come in again with not any prepared material, just there for you to answer questions. If no one shows up by like 9:45, I'll just kill the class and it'll be done. So I
Okay.
want you to use next week to really prepare for that final. If anybody wants, I could, let me see. You'll have plenty of time. I could make the test on Thursday, the final on Thursday, if anybody wants to do that, but I'd have to find a time where everybody's in agreement. So if anybody would like to go ahead and get the test over with on Thursday instead of Friday, the final exam that is, then email me a time on Thursday or several times on Thursday that work for you, and I'll go ahead and make that happen. I can't make up, probably not going to be able to make up 2 tests. If I could make up 2 or 3 different versions, I could have 2 or 3 different times y'all could take it, but I think it'd probably be best if I just stick to one time. So if there's a time like a Thursday, or even I could do Wednesday if y'all prefer, we could knock the test out Wednesday during lab time. So if anybody prefers Wednesday at lab time, that would work. Or you can email me both whether or not you can do Wednesday at lab time, as well as a time on Thursday that you'd be willing to do it, or several times on Thursday you'd be willing to do it. So if y'all want to get out and knocked out early, you can. Okay. All right, so let's start off on chapter 32, which is, again, as I told you, is called elementary particles. You'll see that elementary particles are not necessarily what you think they are, nor are fundamental particles. So it turns out ultimately the definition of fundamental particles is they're the particles that we think are have no internal structure. They're not made of anything else. So when we say fundamental particles, we talk of things that seem to have no apparent physical dimension size-wise. In other words, when we measure them, we get a factor of 10, a factor of 100, a factor of sometimes several thousand smaller than the nucleus. They do not appear to be physical objects that have an extended dimension, left, right, or up, down, or in, out, that sort of thing. So those are the fundamental particles, and the elementary particles are the ones that sort of everything is made of. So you can sort of think of protons, neutrons, electrons, that sort of stuff. But we're going to find out there's a buttload of particles, in fact, and there's tons of them, and they are not very common now. In fact, we have to do some pretty cool experiments to actually get to see them at all. And we didn't necessarily know they existed. In other words, like Dirac, when he came up with his relativistic formula for quantum mechanics, basically a special relativity version of Schrodinger's equation. When he came up with that, he got negative energies, and then he used that to predict the existence of antimatter. So he predicted the existence of the positron, which is the E plus, and he predicted the proton with a negative charge and stuff like that. That was a case where the theory predicted particles that didn't exist. In this case, we end up getting a bunch of particles that we didn't necessarily know exist, and then after the fact, we have to go play catch up and see if we can understand them. So that's sort of what we're going through. So first off, I want to talk about high energy particles and accelerators. So initially, what we did is we wanted to probe the nucleus, and we realized in order to break open the nucleus, we had to do it with a lot of energy. Remember, we found out that the strong force was basically a factor of 100 stronger than the electric force. The electric force being the strongest force we knew of in nature at the time, gravity being the weakest. And then later we found out about the weak force, which is actually weaker than the electric force, but still stronger than the gravity force. But in some ways, it's kind of a weird force. In fact, it gets weaker the closer you are together, but it gets infinitely strong when it's far apart. So some weird stuff like that. So we realized that the nucleus was held together with really strong forces, or you could say high amounts of energy. So in order to break that open and look around what's inside, you had to send it with particles that were really fast. The alpha particle, of course, is what Rutherford used, but you could also use protons, you could use neutrons, all sorts of stuff like that. So we came up with these things called accelerators. And one of the first ones was really these Ds, DEES, at UC Berkeley. And let me show you some pictures of that. So at UC Berkeley, I'm going to do this one here. I'll shrink this a little bit. At UC Berkeley, this is one of the big ones. This is the 60-inch cyclotron. E.O. Lawrence basically created the cyclotron, but his initial one was like, it fit on a table. Your textbook has a picture of the one that fits on the table, but it sort of looks like this diagram right here. So what you have is an actual voltage source that's connected to a hollow ring. So there's a hollow ring. This, I'm talking in 3 dimensions here. So there's a ring around this metal inside, and that's sort of like a capacitor in that it'll have like one side positive, and then this other ring over here, it's got to be hollow because the particles got to go through it. The other ring over here will be negatively charged, but it'll switch back and forth in time. So what you do is you allow a particle to come in, say in the center, maybe it's an electron, and then the electron will be driven across this gap in such a way that it acquires a little bit of speed. But then once it gets across that gap, like, you know, outside of a capacitor, there's not much electric field anymore. So then the electron will actually follow the path due to these 2 magnetic poles. So in other words, you got a magnetic field going into and out of that that disk there. So around here, it'll turn around here. But of course, the faster the electron goes, then the larger the radius would have to be for a given magnetic field strength. But by going in a half circle, it's all of a sudden attracted to the far negative plate, and attracted to the far positive plate, and trying to get away from the negative plate, which happens to be synced up in just such a way that as soon as it gets here, it switches to this side being negative and that side being positive. So the electron jumps across there, speeds up some more. But when it speeds up some more, now it's got a higher velocity, and then the magnetic field causes it to make a curve again, but this time the curve is slightly larger, and it keeps on getting larger and larger and larger, so it can reach, you know, on the order of 95% of the speed of light. Ultimately, after it goes through that cycle several times, it'll be shot out the end, and you'd have a target there, like the nucleus of a uranium atom or something like that. So that's called what we call the Ds. And you can see it says the section of the Ds. These 2 plates right here, the one that's got the little ring around the outside, that would go into the page here. That's what the Ds are. So there's a D and there's a D, and the magnetic field's going through it. That was the original accelerator. They realized that if you made that bigger, you could make it go faster. So they ultimately made, you know, here's one that was 1.5 meters in diameter, or basically 5 feet in diameter. This one's another big one. This is actually in Belgium though. Here's the 37-inch one at UC Berkeley as well. And there's one of the original smaller ones that the E.O. Lawrence had used. So this one was running on 27 megahertz. You can actually work out that frequency, but here's a schematic of basically what we're talking about. So these are the metal plates that are not really plates. Again, they're sort of rectangular hoops of wire going into the page here, and they will get positively charged and negatively charged so that the electron will accelerate towards them on one side, and then the opposite direction on the other side, and then the opposite direction on the other side, and so on and so forth. So that's what the cyclotrons were. They were the earliest accelerators. And it turns out that when you do that, you can basically examine stuff better so than when you do it with light. So for instance, when you use a microscope, you can look and magnify really, really close up and see very small details. But the problem is light doesn't interact with particles or anything unless the size of the particle that you're trying to study is bigger than or about the same size as the wavelength of the radiation you're using. Well, you know, for instance, that visible light only goes from about 400 to 700 nanometers. So you can't see, and technically there's no such thing as seeing, period, anything smaller than 400 nanometers. That being said, we can still sort of take something that's smaller. If we have something smaller than visible light to probe it, we can get a shape of the structure and stuff like that and render that as a drawing, but you're not physically seeing it anymore. So if you think about that, let's say an electron, and I think that's what I want to use, an electron maybe. Yeah, let's say we have a 2 gig of electron volt electron. I know you're not looking at the document cam right now. I'm just writing it. So let me switch my camera to the document cam. And again, we're going to imagine having a 2 giga electron volt. If you want to do like Back to the Future and pronounce it giga, I pronounce it giga, as in like giga frog. So a 2 GeV electron. What we'd like to know is, what is the resolution? So the resolution really means basically from diffraction limiting that we studied earlier in optics, that it turns out the resolution is really a function of the wavelength. So you can see things about as small as the wavelength of the stuff you're probing it with. So really what we're asking here, when I say is what is the resolution, resolution, what I'm really saying is what is the wavelength? Well, at 2.0 GeV, that's actually the energy of the particle. So when they talk about something having an energy of 2.0 GeV, for instance, what they're really saying is that basically you have a kinetic energy equal to let's say 2,000 MeV. Now, the reason why I put it in MeV is we can get a little closer to the electron mass. The mass of the electron, remember, is 0.511 MeV per c squared. So we see already that this is several thousand, in fact, it's about 4,000 times higher than the rest energy of the electron. Whenever you get a appreciable factor larger than the rest energy of a particle, then that means you have to use relativity. So relativity told us that E squared is equal to P squared C squared plus M squared C to the fourth. So if we want to actually know the wavelength, we have to use de Broglie's relationship, which lambda is equal to H over P. But P is not just MV anymore. It turns out this equation is still accurate even when we're dealing with relativity. It's just you have to use the relativistic P, and that's that P that's over there. So if you solve this for P, first thing you want to do is multiply by C squared. So I get divide by C squared. So I get E squared over C squared is equal to P squared plus M squared C squared. Now I'm going to subtract M squared C squared from both sides, and I'll get E squared minus, and I'll rejigger it a little bit, M squared C to the fourth over here over C squared is equal to P squared. Okay, so ultimately I can get P is equal to the square root of all this junk, which is the square root of E squared minus M squared C to the fourth, square root of all that, over square root of C squared is just plain C. Well, when you look at that, you realize, hey, wait a second, this E that we were talking about really is, I said kinetic energy, excuse me, the plane energy here that we were talking about is like 2,000, right? And that's, again, 2,000 MeV, whereas this is like 0.511. So you might as well say this is essentially equal to E over C. So lo and behold, that is what the momentum is. So we're going to say the momentum, and therefore the resolution of this is H over P, which of course equals HC over E. So now we can use our constant H, which is 6.63 times 10 to the negative 34th joule seconds for H. 3.00 times 10 to the 8th meters per second for the speed of light. And then E, the energy, we're going to actually have to convert that back to actual joules. So I'm going to say 2.0 times 10 to the, remember, kilo is 3, mega is 6, and giga is 9. So 2.0 times 10 to the 9th. Electron volts, and then we realize that 1 electron volt is 1.602 times 10 to the negative 19th joules. So we have to multiply by 1.602 times 10 to the negative 19 joules per electron volt. Okay, so that's the math that we got to actually do. I'm going to pull out my calculator and do that. 6.63 e to the negative 34 times 3 e to the 8. Now I'm going to divide all that, and I'm going to use parentheses because remember, your calculator is good at knowing its order of operations. So if I divide by 2 times 10 to the 9th multiplied by 1.602 times 10 to the negative 19th, it's going to only divide by the 2 times 10 to the 9th, and then it's going to multiply by the 1.602. So we don't want that. So I'm going to divide by, in parentheses, 2 e to the 9th times 1.602 e to the negative 19th. And then I'll close my parentheses, hit enter, and I get 6.2 times 10 to the negative 16th meters. So in this case, we're getting quite a bit smaller even than the nucleus. Remember, the nucleus is about 0.5 times 10 to the negative 15th meters or so. We're actually at 6.2 times 10 to the negative 16th. So we're able to really probe the structure of the nucleus at that point. That's a really, really small amount. You can even use the femto or the Fermi meter. The FM unit, of course, is 10 to the negative 15th. So if I multiplied this by 10, that would make it 10 to the negative 15th, but I have to divide this by 10. If I divided this by 10, that would make it 10 to the negative 15th. And then I have to multiply this by 10. So we could say this is roughly 62 femtometers. I think that works out right. So it's quite small, in fact. Oh, no, I think 15. Yeah. Scratch this femtometer part. I think I might have made a careless mistake, but anyways, we'll leave that alone. But this turns out right. So that's one of the reasons that we can use these particle accelerators and why we get them at such a high energy. You can see that the wavelength and the energy are inversely related. And since the wavelength and energy are inversely related, that means the higher the energy, the lower the wavelength. Remember, these relationships are what I call thumbs up, thumbs down. So that's really helpful. So if I want to probe deeper and deeper, I got to make a lower and lower energy. Any questions on that? So that cyclotron worked really well, and you can work out the details of how it works pretty straightforwardly. We know that Newton's second law says the summation of the forces is equal to mass times acceleration. In this case, we're really just talking about a force acting centripetally, something going in a circle, right? So the acceleration in that case is v squared over r, where v is the velocity that it's going, divided by r, the radius of the circle that it's going in. And then, of course, the force law is the Lorentz force law for just the magnetism part. So F equals QVB sine theta. But in this case, B and V are always perpendicular, so the sine theta just becomes 1. You don't have to mess with it. So ultimately, we get QVB is equal to M times V squared over R. Obviously, one of these V's can cancel out. And that allows us to actually solve for the velocity. That tells us the actual velocity would equal QB over R, over M, and then QVR, QB times R over M. So that's our velocity. The reason why I'm doing that is I'm trying to find out what frequency I need to actually turn on the positive to one side and the negative to the other side, and then flip that back to the negative on the first side and the positive on the other side. So we know that the period is equal to basically the time required for it to go in a complete circle. Well, period is time, velocity equals distance divided by time. So time would equal velocity divided by distance. Let me see if that works right. No, time would be distance divided by velocity. Well, the distance around the circle is 2 pi times the radius of the circle. And of course, we've got the velocity being QB R over M. So we can see that the R's ultimately cancel out, and I get QB, I get 2 pi M over QB. So that's the period, that's the time it takes for, in those D's, that's basically the time it takes for the electron, say, to go from here through this gap and then here. Okay, remember the gap sped it up a little bit. So since the gap spread it up a little, speeded it up a little bit, that's going to make the radius slightly larger. So what I want though is the frequency, and the frequency is in fact 1 over the period. So 1 over the period gives me QB over 2 pi times M. So that's what we call the cyclotron frequency. So let's think about the one that we talked about at the UC Berkeley. Let's do the 5-foot one, the 60 inches. That's a diameter about 1.5 meters. So in that case, we have a radius of 0.75 meters. And let's say the magnetic field is about 2.0 Tesla. So B is equal to 2.0 Tesla. And let's say we want to accelerate a proton, and we want to find out what the frequency needed for that and the kinetic energy of the protons. So what we have is the particle Q is has a charge E. Notice I just wrote E, not E minus. So that's 1.602 times 10 to the negative 19th coulombs. And it has a mass M sub P of, and you can look up the proton mass, it's 1.67 times 10 to the negative 27th kilograms. So we should be able to calculate the frequency of the cyclotron radiation there, or the cyclotron frequency. So F is actually equal to QB over 2 pi M. Well, Q is 1.602 times 10 to the negative 19th coulombs. B is 2.0 Tesla. 2 pi is, of course, 2 pi, and then the mass is 1.67
Professor,
times 10 to the negative 27th.
Professor
Yes,
Younger,
ma'am.
we can't really see. I think there might be a bandwidth issue.
Yes.
It's making it a bit blurry.
Okay. Let me do that again then. Okay. So these were the, I want to put this just for the record, so in case anybody needs it, they can see it later. So this is the first problem we solved. We had a 2 giga electron volt electron, and we want to know what the resolution of that setup was. The total energy was 2000 MeV, whereas the rest energy 0.511 MeV per C squared. That tells us that the energy is way, way, way higher than the mass energy. So the mass energy, so it has to use relativity, which is why we use E squared, P squared, C squared, M squared, C to the 4th. We also had to use the de Broglie wavelength because the wavelength is really what the resolution means. So working through all that, we were able to find 6.2 times 10 to the negative 16th femtometers, or excuse me, negative 16th meters. And I tried to do a femtometer thing. I think I made a mistake, so I just X'd that out. This problem, we were working Newton's second law for the electrons in a cyclotron, or for the particles period in a cyclotron. We knew that the centripetal acceleration was v squared over r. We know that the force is QV sine theta, but B and V, the magnetic field and the velocity, are at perpendicular angles to one another. So sine of 90 is 1. So I use those in Newton's second law. I got QVB equals MV squared over R. That allowed me to solve for V. V was QBR over M. I'm going ultimately for finding the frequency at which I need to flip those voltages on the capacitor. And to find the frequency, I can first find the period. And the period is really the distance divided by the velocity. Well, the distance going in a circle is 2 pi R. The velocity is QBR over M. So I ended up getting 2 pi M over QB. Notice the R's cancel out. That was the period. That's the time required for it to go from here all the way around here and then back to that same spot again. I didn't draw that last little jump across the space. The frequency is 1 over the period, so I just flip those, and that's the cyclotron frequency. And now we're trying to solve the problem of the 60-inch cyclotron at UC Berkeley, the radius of which is, since 60 inches is about 1.5 meters, the radius would be half of that, which would be about 0.75 meters. I'm assuming that it had a magnetic field strength of 2.0 Tesla. We're going to accelerate electrons, so the charge is positive E, 1.602 times 10 to the negative 19th. And the mass of the electron is 1.67 times 10 to the negative 27th. And I'm just blindly plugging it in that formula, QB over 2 pi M. Okay. So now I got to do those calculations. Hopefully holding it close enough there will allow y'all to pause the video at any point and get those numbers. I appreciate the bandwidth reminder because I didn't notice it on my side. That's 1.602 10 to the negative 19th times 2. And then I divide by, again, remember to use your parentheses when dividing by products, because otherwise the first number in the product series will be both divided and all the other ones will be multiplied. So I'm going to do parentheses, left parenthesis, that is 2 times pi, which I have a nice little button for pi, times 1.67 e to the negative 27th. And then I close parentheses and hit enter, and I get 3.05 times 10 to the 7th hertz is the cyclotron frequency. That's basically around, let me see, that's about 30. If I multiply this by 10, actually, if I divide this by 10, I'll get 10 to the 6, which is a megahertz, but I have to divide that by 10. So that's 30.5 megahertz, which is well within the radio wave region of the electromagnetic spectrum. If I wanted to find the actual speed at which the proton leaves, basically all I have to do is find the velocity and calculate the kinetic energy that way. So I'm ultimately looking for the kinetic energy. Kinetic energy equals 1/2. And again, I'll pull this up towards the camera when we're done. It equals 1/2 mv squared for non-relativistic particles. We're going to assume for a second that it's non-relativistic. If we find out that the energy is bigger than or comparable to the rest energy of the proton, then we'll know we did it wrong. Otherwise, we'll just go on with it. So what we know is V is equal to QBR over M. So this becomes 1/2 M times Q squared, B squared, R squared over M squared. Obviously, you can make a lot of simplifications, and ultimately you get Q squared, B squared, R squared over 2M. Only one of the M's is going to survive. And now I can put in all that stuff, which I'll leave out for right now. I mean, you know what it is. You know that's 2. You know that's 0.75. You know that's the number 2, of course. You know that's the 1.67. I'm just going to crunch this out and say 1.602. And I'm doing this for saving space, but like I said, I think you can figure it out. But that's 1.602 times 10 to the negative 19th. I'm going to square that. And then I'm going to multiply that by B, which is 2.0. I'm going to square that. And then I'm going to multiply that by R, which is 0.75. I'm going to square that. And then I'm going to divide by, again, using my parentheses, 2 times 1.67 e to the negative 27th. That one does not have to be squared. And I get 1.73 times 10 to the negative 11th joules. I can now convert that to electron volts by dividing by 1.602 times 10 to the negative 19th. When I divide that by 1.602 times 10 to the negative 19th, I get basically 107 or 108 mega electron volts. If you remember, the rest mass of the proton was like 938 mega electron volts. So this is a ninth of that. That means using non-relativistic physics was just fine. So we now know that the kinetic energy coming out of that is about 108 MeV. Now I just saw a notice that my internet connection is unstable. So I want to show you this a little bit closer. Let me hit the focus thing. So we found the frequency turned out to be 3.05 times 10 to the 7th hertz, which is about 30.5 megahertz. I said that's in the radio part of the electromagnetic spectrum. To give you some idea, remember if you listen to, for instance, 93.7 FM, 93.7 FM is 93.7 megahertz. So this is about a factor of 3, a little bit more than a factor of 3 higher than that radio station. And that's the signal that that radio station puts out, by the way. That's what we call a carrier wave. And then there's a smaller wave that's the actual sound built onto that. And since it's FM, it's frequency modulated. So it's actually multiplied by the frequency. So the waves looks like they're going squishy, squishy, squishy. So the high frequency parts of the sound would have the waves really closer together. The low frequency parts would have the waves stretched out like that. AM is amplitude modulated. So that makes the waves go vertically up and down like that. Anyways, back to the particle, back to the electron coming out of the 60-inch cyclotron. We know that we have to run that at 30.5 hertz. Notice it didn't depend on the radius. That's the key point, because not having the radius means you use the same frequency no matter how big it gets. So you just keep doing that over and over and over, and it's going to keep making the particle go in the right direction, speeding up each time, each little small interval. And that gap is so small, you don't have to deviate much. You could actually do a second order calculation to correct for the fact that it's not exactly a circle, but you find that you really don't need to. The final part of the question was, what is the kinetic energy of the protons that actually leave that? Well, the kinetic energy, assuming it's non-relativistic, is just 1/2 mv squared. But we'd already determined that the velocity was qBr over m. So I plugged that in, and I got 1/2 m times q squared b squared r squared over m squared. Because that's the velocity squared, this part right here. Simplifying, that gives you q squared b squared r squared over 2m. I didn't show me putting in those individual numbers because you really don't need to. I think you can tell that q is 1.602 10 to the negative 19th. B is 2.0 Tesla, R is 0.75 meters, and then the M at the bottom is 1.67 times 10 to the negative 27th kilograms. That gave me 1.73 times 10 to the negative 11th joules, which I converted by dividing by basically that number, because that's the number of joules per electron volt. So when I divided this by that number, not that unit number, but that number, I got 108 MeV. So that tells us that the particles have a kinetic energy of 108 mega electron volts. That was a factor of 9, almost 9, smaller than the rest energy, i.e. the rest mass of the proton. So we know it was okay not to use relativistic kinetic energy. Any questions on that one? All right, so here's the problem. When you actually make that accelerator and you're accelerating charged particles, which you have to with that particular type of accelerator, you have to accelerate charged particles, because charged particles are the only ones that speed up as a result of a voltage difference. So you couldn't do neutrons in there, for instance. You certainly couldn't do neutrinos, which is a whole different story. But anyways, you couldn't do neutrons. So doing that, what you're forcing is charged particles to travel in a circle. and they're traveling in a circle, but they're also speeding up in between the Ds. While they're speeding up in between the Ds, they're accelerating, even though they're going straight. They're just speeding up. So that's still an acceleration. And then when they're going through the Ds, which is when they're going in that arc, if you will, due to the magnetic field, in that case, they're accelerating too, even though their velocity is not changing. And Maxwell's equation taught us that whenever a charged particle accelerates, we know that it's going to get off radiation. In other words, radiation is going to come out from that, and that's called synchrotron radiation. The problem with that is it doesn't have anywhere for the energy to come from. You know, a photon, for instance, could lose energy without speeding up or slowing down, because a photon always travels at the speed of light. It would do so by decreasing the frequency, maybe. But electrons don't necessarily behave that way, neither do really photons, to be honest with you. So ultimately, it has to lose some of its speed just by accelerating, just because it's accelerating. So that's a problem. So you might look for another type of accelerator, in which case you look for, say, a linear accelerator. And that's what, you know, SLAC, it's the Stanford Linear Accelerator Center. That's what that stands for. And that's a straight line accelerator where you're only going to lose radiation as a result of speeding it up or something like that. Again, that's the whole purpose of the thing. So you don't expect any problems from just speeding it up. But you can just make it so big that it doesn't matter and you keep on. But the problem is you're always going to be putting off radiation. So, you know, accelerators are not places where you just hang out and drink coffee and stuff, at least not near the beam, because that's constantly putting out radiation. And sometimes that radiation is not necessarily safe for you. Some of those accelerators, as you saw in that case, we had 108 MeV acceleration from the cyclotron at Berkeley. That's not very appreciable. In fact, you're going to get speeds that are, you know, nowhere near the speed of light. That's not very helpful. So you want them faster and faster, higher and higher energy. Modern accelerators are in the actual tera electron volts. There's an accelerator called the Tevatron, for instance, that runs on TeV, which again, it goes kilo, mega, giga, tera, and so on and so forth. You can keep going up and up and up. But that's a whole nother factor of 1,000 higher than a giga electron volt. So you can see that we go send accelerators, send particles at an extremely high speed. So one way they do this is they bury the accelerators underground, and then they have a series of things not unlike the Ds. Specifically, you'd have, for instance, like a little tube right here. So it's a hollow tube, if you will. And with that hollow tube, you maybe have a source right here that maybe puts out electrons. If it's putting out electrons, then you want this to be positive, so the electron will be fired that way. Now, have it being a tube, a circular tube, and having the electron source lined up dead center, the electron has no reason to go up or down or left or right. In fact, it's only going to be attracted to going straight down the center, and therefore it won't hit it, okay? But then, as it speeds up by going through here, you can actually put out in front of it, or it speeds up as getting to it, you can actually put out in front of it another tube, and this tube will be a little bit longer. And that tube will actually be, say, negative, and so on and so forth. And you can actually use this for whatever type of particle you have, whether it's a positive particle or negative particle. You just got to speed it up at the first instant. And then each subsequent tube will become longer and longer and longer. And in so doing, it'll speed the accelerator up. So that's how the linear accelerator works. If you want to look at, for instance, a nonlinear accelerator like what we have at CERN, the Large Hadron Collider and things of that sort, then you can look at some of these pictures. I think this one is actually, I don't think that's CERN. I want to say this is the Fermilab one. Yeah, that's the Fermilab one. So I've actually flown. If you've ever flown into Chicago, you probably flew right by this building. It looks like a space shuttle hangar or something like that. So if you fly into Chicago, I think it's Chicago's O'Hare Airport, you'll actually see this. And this whole circle here is an accelerator. That's the Fermi Lab that was basically created and named after Fermi, Enrico Fermi, who we talked about earlier. So those are some of the types of accelerators you can deal with. You can also look at the one in CERN, which is the Large Hadron Collider. Here's a picture of inside the tube. So you can actually walk around. So this tube is a vacuum tube, basically. It's gotten rid of as many particles as we can here on Earth. And then through it, we've got all these devices that cause the electron to speed up and magnetic fields to make it bend so that it goes in a circle and so on and so forth. This is another picture of the Large Hadron Collider right here. And you can walk by this if you really wanted to. The problem is when the accelerator is running, you don't want to walk by that because you've got charged particles putting off buttloads of radiation. And in fact, if you go anywhere near it, you're supposed to be wearing a radiation badge. And then, of course, you've got to detect these things. And that's where the really cool part is. We have, for instance, the Atlas detectors. Notice these are human beings standing in front of this thing, and look how big the sucker is. So even though these electrons, which are, and protons and neutrons, hadrons are you know, protons, neutrons, that sort of stuff, even though they're so small, this is how big a detectors you have to have. And they basically track the paths of everything. They get graphs that look like this guy right here, which is lines that are straight, lines that are curved, and that's like one collision event. So that's what the detectors do, is they basically catch the images of all the particles. They have bubble chambers, and the bubble chambers basically are a sort of liquid that whenever a charged particle goes through it, it leaves a string of ionized atoms or molecules, and those ionized atoms or molecules form bubbles, and you can actually follow the bubbles, and knowing basically how far the bubble traveled and X amount of time, you can tell exactly their speed and energy. If they curve one way, you know it's due to the magnetic field, and therefore they have a positive charge, or if it curves the other way, it have a negative charge, or if it doesn't curve at all, you know it's neutral, in which case you're not going to get any bubbles, of course, but still you can tell that. And at the end of all of it, you can analyze it and ultimately figure out, hey, I just saw the Higgs boson, which is really one of the main things the Atlas detector as well as the Large Hadron Collider was searching for. So that's some of the cool stuff that these accelerators do. Your pictures got some, your book has some cool pictures of the Atlas detector as well as the Large Hadron Collider, which is in CERN, by the way, Switzerland. So you can see all sorts of cool pictures of these, and these things are literally miles across. I think the Large Hadron Collider is like 26 kilometers, which would be, you know, on the order of 20 miles across. So it's kind of a big deal. And some of them, they have small accelerators that speed them up just to get them fast enough to go into the main accelerator. So it's kind of cool stuff. I'll stop sharing my screen now. So I said stop share. Okay, so we've seen basically there's accelerators that go in circles, and then there's accelerators that go in straight lines, and probably the best one for a straight line is at Stanford. That's the Stanford Linear Accelerator, and of course the highest power one for a circle right now is really the Large Hadron. Excuse me. The Large Hadron Collider. And the Large Hadron Collider, like I said, needed to be that high of energy because not only are we trying to study the Higgs boson, which means you need to break up the hadrons into smaller and smaller bits by using higher and higher energy. And the Large Hadron Collider basically can produce two colliding beams at 7 TeV each for protons. So you basically get a total energy of 14 tera electron volts. So that's a really, really big deal. Just as a reminder, so I told you it's kilo, mega, giga, tera, and then beyond that it's peta, exa, yeta, and yoda. Yoda. Oh, you boss. All right. Anyways, let me do another calculation for you. This one's protons basically moving at relativistic speed. So what we like to do is sort of get an idea of why it's so hard to accelerate particles. So imagine first that you accelerate a particle, let's say in this case, will accelerate a proton to, let's say 90% of the speed of light. Let's say 99% of the speed of light, and then we'll do 99.99% of the speed of light. So if we want to do that, we're going to say, so the mass we have is the proton, and we know that's 1.67 times 10 to the negative 27th kilograms. Of course, we could also use the mass of the electron and MeV per c squared. That's 938.57 MeV per c squared. Yeah, I was just double checking that I had said the electron right. So that's the mass of the proton. What we want is V to equal 99% of C, or 0.99 C. That's part A. And what we want to know is how much work it takes to do that. So that's what we're looking for in part A. And then part B, we want to know how much work it takes to go the extra 0.99. So we want V to be 0.99, which is what it was before, but 2 more nines, C. And we want to, again, find out what the work / energy for that is. So it turns out we can use the work energy theorem, and the work energy theorem basically says that any work you put in is really equal to the change in kinetic energy. So work is equal to delta KE. That's the work energy theorem. And for relativistic particles, we know that the kinetic energy is equal to gamma minus 1 times mc squared. In other words, well, I'll just leave it at that. Just realize that when I multiply 1 by mc squared, what I'm really getting here is the rest energy, and then the gamma's accounting for it, the total energy. So the relativistic factor gamma is equal to 1 over the square root of 1 minus v squared over c squared. That's what that gamma corresponds to. So if I want to actually find out the work required to get up to 99% of the speed of light, I'm going to say work is equal to change in kinetic energy, which equals kinetic energy final. So what I'm saying is KE 0.99 minus KE 0. Okay. So that really is gamma minus 1 for 0.99 m proton c squared minus gamma minus 1 for 0 of mc squared. Okay. So we now can actually calculate what the work is. The gamma for 0.99, and I'll actually just calculate this real quick. I'm going to do it up here. So gamma 0.99 is equal to 1 over the square root of 1 minus 0.99 c over c. That quantity right there is squared. So you can see there's a c in there, by the way. So when I calculate that, I'm going to do the other one too next for 0.99. I'm going to do 1 minus 0.99, and I'm going to square the 0.99. That's 0.0199. Now I'm going to take the square root of that. And now I'm going to divide 1 by that. And I get 7.08881. Now gamma 0.9999, okay? In that case, I want to take 1 minus 0.9999 squared. I get 0.0002. Actually, I get more digits than that, clearly. It's probably 1999999, so on and so forth. Now I'm going to take the square root of that. I get 0.014142, so on and so forth. Now I do 1 divided by that, and I get, in this case, 70.7124. So you can see the gamma goes up a huge amount in going from 0.99 to 0.9999. So it literally went up by a factor of 10 about. Okay. So now I've got all that worked out. I can say this is going to be equal to gamma 0.999. That'll be 7.089 minus 1 times, I'm just going to use the MC squared. I'm going to use the 938.57 MeV per C squared times C squared. So I'll automatically get everything out in MeV. That's just this first term. The second term, by the way, is gamma of 0. Obviously, that's a 0 in there. 1 minus 0 is just going to be 1. Square root of 1 is just going to be 1, and it'll be 1 over 1. So I just get 1 minus 1 times 938.57 MeV per C squared times C squared. So this whole part right here is just 0. So I ultimately get just 7 times the the proton mass rest mass energy. So 938.57 times 7.088. That gives me 6.653 GeV. In other words, it came out to 6,653 MeV, but I went ahead and moved the decimal 3 places and made it into GeV. So the actual work required to speed this thing up was about 6.6 GeV. Now, in going from this speed, this 0.99 to the other speed, 0.9999, the work is going to be given by the same formula. So in this case, the work is delta KE again, but in this case, it's going to be gamma 0.9999 minus 1 MPC squared, which I'm going to replace this whole thing with just 938.57, minus, in this case, the gamma 0.99 minus 1 MPC squared, again, replacing that. So what I get in this case is 70.7124 minus 1 times 938.57 MeV. I'm not sure if I actually subtracted this one now in retrospect, so I might be off by a little bit on this one, but y'all might want to check that. I don't remember subtracting the 1 now like I was supposed to, but we'll see. It's not off by much either way. It's off by, well, 938 MeV, so it would be a 9 there basically would be off by, so it could be 5.753 GeV approximately. So I just put that there just to remind you guys. Mr. Younger's an idiot. He might have forgotten to take away the 1 because he got so excited about this, having the 7.09 already worked out. So the same thing's going to work out here, and then minus, in this case, it was 7.0. This is why I was checking it, 7.089 minus 1, 938.57 MeV. So now it's time to pay the piper. We'll find out, in fact, whether I was right up there with this number or whether I was right initially and then actually subtracted it. So I'll do 70.7124 minus 1. That's 69.7124 times 938.57 MeV. I get 65.43 GeV. Again, I moved the decimal. It was 65,430. So I moved the decimal 3 places to the left and made it GeV instead of MeV. And that's just this first part. Now I'm going to do this one. This is where I'm going to find out if I was supposed to be closer to that figure. So I'm going to do 7.089 minus 1. And then I'll multiply that by 938.57. And lo and behold, I do get 5.7. So yeah, I forgot to subtract the 1. So let's do this. No, the actual answer is 5.714 GeV. So the 5.7 part was right. So this is the actual answer. And that turns out to be what this is as well. So it's 5.714 GeV. So I'm going to do 65,430 minus 5,714. And I get, lo and behold, 59,000.72 GeV. So it took about 5.7 GeV to get up to 99% of the speed of light, but it took almost 10 times as much, actually more than 10 times as much, to get from 0.99 to 0.9999. So I think you can see the faster you get, the harder it is to go faster. And that's why we believe anything with mass is going to require an infinite amount of energy to actually get us up to the speed of light. So nothing with the speed or with a mass greater than 0 is ever going to get us to the speed of light. Okay? So that's a typical problem that you should be able to solve as well. These are, again, making examples that are sort of like the ones the book did, and those are the ones that I think are most appropriate for you to be able to pull off for chapter 32. The final exam, like I said, is going to cover all that material that the final exam said it was going to, plus what was test 5. It's going to cover 32 and 33, but very, very lightly. Maybe one or two problems total for 32 and 1 or 2 problems total for 33. I'm also going to make the final exam. Some people have mentioned how it's kind of a bummer when you do a multiple choice test, having so few questions. If you miss one, you're already in a B category. So that's a bit of a problem. So I am going to actively try to make it more problems and give you more time for the final. Okay. Don't forget to email me and let me know whether you'd like to take it Wednesday during lab time instead of Friday during lab time. I'm thinking most people might want to go ahead and get the course over with that way. I will still be available for Friday because I can't rip you off class time if you want, but we can just plan on having it Friday if y'all prefer, or you can even do it Thursday if you prefer. But I'm definitely going to give you Monday during lecture time and Wednesday during lecture time. I'm going to give you time to ask questions about any past problems we had to work, and so on and so forth. Okay. All right, so now that we've worked through the aspects of particle accelerators and things like that, I'm going to start telling you about how we think of forces in terms of quantum mechanics. So remember when we were going through quantum mechanics, we thought of light as a particle in terms of Newton's equations. So Newton had worked all of the laws of optics, basically. It worked those out as if light was particles. And Huygens and Fresnel and all these people come along and they work out all that stuff and other stuff as if light is a wave. And then ultimately we have to decide that basically light is both a particle and a wave. Well, it turns out we can think of the force as if there's literally a force in terms of gravity or in terms of the electric force. And we did this with the electric force. We didn't like the idea of a proton, say in the nucleus of an atom, reaching across space without physically touching it, but still reaching across space and not touching the electron, but applying a force to it. That was called action at a distance. It was a bit of a problem. So we took an intermediate step, and that intermediate step was we're going to imagine that the proton alters space by creating a field. So space was altered a little bit, and then the electron interacts with the field, which it has to be touching because the field goes over all space. And it turned out that that was not only a good way of dealing with the action at a distance, but it turns out that we could make predictions about things about the field, and they turned out to be right, so we think the field exists. So the field is something that occupies all space, which is not unlike what waves do. You know, particles are isolated small parts of space, whereas a wave is actually a field over space. It's some wiggling that's traveling in space, but it covers a big chunk of space. So it might seem reasonable, since we think that particle or light, which is both particle-like and wave-like, it might be reasonable to think that fields might be both particle-like and wave-like. And that brings us to quantum electrodynamics. And quantum electrodynamics, which was largely made a lot simpler by Richard Feynman, basically sees this. You can think of, let's say, a positron, let's say 2 electrons. Let's say E minus is traveling along this way, and then another E minus, of course, is traveling along this way. Well, you know that these two are repulsive. So what might happen is this thing goes like this and then curves and goes like that, where this thing's going to do the same thing, curve and go like that. That's really what's going to happen to them. We can think of this as if it's a force acting between them. We can think as if this one's creating a field that covers all the space, and then this one's interacting with the field. But what quantum electrodynamics says is, no, there's actually a particle exchange. So you might think, in fact, that this particle or this electron gives off a force-carrying particle, and in so doing, just like if you, let's say you're on a frozen lake and you're sliding along this frozen lake on ice skates, if you take a car battery that you were holding and throw it to the right, you're going to recoil, not unlike a bullet, causing a gun to recoil, and you're going to coast off that way. Similarly, if your friend's skating beside you and they catch the car battery, God help them, then they're going to actually be deflected that way as well. So you can think of this as if it's a force, and then you have action at a distance. You can think of it as if this thing's making a field and this thing's interacting with that field, or this thing's making a field and this one's interacting with that field. Or, and this is the ultimate one, we can think of this thing generating a virtual particle, in this case it turns out to be a photon, that is shot off this way, and because it's shot this way, the electron recoils that way, and it hits this electron and causes it to recoil this way. So that's really basically what we treat the electric force as. This is time axis, and this is the position axis, or the x-axis, you might say. And this is called a Feynman diagram. If you watch Big Bang Theory, you'll see these in the background all the time. They're Feynman diagrams. And there's a lot of different ways this can occur. This is like the most probable, and therefore the one with the highest energy, and so on and so forth. So it makes the most sense. But Feynman was able to make sense of quantum chromodynamics by these diagrams, which are infinitely easier than the god-awful way that the other people came up with. So life is a lot better with this. Now, in this quantum chromodynamic or electrodynamics, basically we think of these as particles that are used to mediate or carry the force. And I'm going to stop and talk about that in a second, but I'm getting a call from someone that might be very important, so I'm going to use this time to give you guys a break. Let's meet back at 11 o'clock. I won't be available this time because I've got to figure out what this call is about. Video. We were talking about these virtual particles as being a way of picturing the forces going on. Your book actually talks about how you can imagine two rollerbladers passing pillows back and forth. So when a rollerblader on the right throws a pillow at the person rollerblading on the left, the person on the right is obviously going to recoil a little bit to the right because of his throwing of the pillow. And then when the person on the left catches the pillow, he's going to recoil a little bit to the left. So that's how you could see repulsion. If you want to see attraction, you could imagine one of them trying to grab the pillow of the other, and when they pull on it, they pull each other together. So that's another way of looking at it. So this was the way we thought that we could ultimately sort of unify the forces. We realized that quantum mechanics is this big thing in nature, that it's something that we have to deal with, and this was a way that we could quantize the force, the electric force. We could also then quantize, thanks to Yukawa, we could quantize the strong nuclear force and maybe even the weak nuclear force. And then ultimately what we'd ideally want to do is quantize the gravitational force. That last bit has not gone so well. No one's actually figured out a way to quantize the gravitational force, but the strong force was actually kind of neat. So remember I called this a photon, a virtual photon. And what that means is it's not like an everyday photon that you could necessarily catch, which sounds a lot like a way of what Carl Sagan argued was a dragon in my basement. There's an argument where he says, hey, I've got a dragon in my basement. This kid says that. And Carl Sagan says, cool, I'd like to see it. He said, well, he's invisible. You can't see it. And then Carl Sagan said, well, that's okay. I'll just throw some flour down on the floor so I can see his footprints. Oh, no, he floats above the ground, so he doesn't do that. Oh, well, that's fine. Then Carl Sagan says, I'll just take and fill the room up with some smoke like you do in a dance hall or something like that. He said, oh, no, he's immiscible. Well, eventually you got to reach the conclusion that there's no test this person is going to allow you to determine whether or not there's a dragon. And by saying it's a virtual photon that you can't detect, sounds like that. But it stops shy of that because we actually have predictions that we can test and that should suggest it's there. And ultimately we have. So Yukawa does the same thing. Yukawa says, okay, well, I know from quantum mechanics that the uncertainty in the energy times the uncertainty in the time is on the order of or greater than h over 2 pi. That's what we called h bar before, of course. But anyways, what that means is you can have an uncertainty in energy multiplied by an uncertainty in time, and as long as that value is greater than or approximately equal to 2 pi, then everything's fine. And I mean, even violating conservation of energy, you can have that uncertainty that allows for the non-conservation of energy, and that'll work out fine. So let's say, for instance, that the conservation or that the energy difference, the change in energy, is equal to the mass of some particle that we're going to call the carrier particle, or the mediation particle for the strong force, times c squared. So that's the rest energy of the mediator for the strong force. And then that time that's going to happen is basically the time it takes for the particle to travel from here to here in the case of the strong force. So in the strong force, this would be like a proton and a neutron attracting each other. We know that the strong force doesn't reach any further across than about 10 to the negative 15th meters, or let's say 1.5 times 10 to the negative 15th meters. So we could use that as a distance. Well, if that's the case, then the time would be the distance divided by the velocity. And that particle, we're going to suppose, since this one turned out to be a photon, which had zero mass, it traveled at the speed of light, we can assume this particle might, in fact, travel roughly at the speed of light. So that would be our uncertainty in time. That would be our uncertainty in energy. I know there's a little weirdness with that mass being non-zero here, but we're just taking a check that it's going to travel very close to the speed of light. And then we're going to say that's approximately equal to, in other words, it's the best case scenario, approximately equal to h over 2 pi. If you do that, you can actually get an idea for what the actual mass would be. You could say mc squared, which again, that gives you like MeV or KeV or GeV or something like that. per C squared for just mass, but it gives you KeV or MEV or GeV for the whole thing. So you can, just use that just as well. When you do that, you end up getting HC over 2 pi D. So if we go ahead and calculate what that should be, we would think that the carrier particle for the strong force should have a rest energy, MC squared, that's about equal to 6.6. That's the Planck constant, 6.6 times 10 to the negative 34th joule seconds, times C, which would be 3.0 times 10 to the 8th meters per second, over 2 times pi times D, which I'm going to say is 1.5 times 10 to the negative 15th meters. Again, that's roughly the distance across a large nucleus, if you will. If you do all that math, lo and behold, what you'll get is about 2.1 times 10 to the negative 11th joules, which is about 130 MeV. So what Hideki Yukawa suggested was that the carrier particle for the strong force was a particle whose rest mass should be around 130 MeV per C squared. That's again roughly, let's say 1/6, 1/7 of the rest mass for the proton. Okay, but it's not a massless particle, and ultimately that should be a meson, and that meson particle ultimately turns out to be the W0 particle. The W0, the W plus, and so on and so forth, or Z0, excuse me. So that was an estimate of how we could talk about the strong nuclear force. And the carrier particles now become, I'm going to give you a little write-up of basically what's going on. So we have, in terms of our forces, we have the strong force, let's call it strength just 1, so we can put everything relative to it. That's the strongest of the forces. The particle for this guy, we're actually going to call a gluon. So that was the particle we were just talking about. That's the gluon. Okay, and you can see that's roughly sounds like glue. So that was the whole purpose of them using that phrase. So it's a lowercase g is the symbol we use for it. It should be capitalized. It's a name, so I should have wrote capital G-L-U-O-N. So that's the gluon. We found the electromagnetic force. That's about a factor of 100 weaker than it. So we'd say that's 10 to the negative 2 because it's 1 over 100. The particle that carries that is the photon. And that has the symbol of a gamma particle. It's just a gamma. Then there's the weak nuclear force, the one that Enrico Fermi suggested to explain beta decay. When these things interact, there's different conservation laws that don't actually kick into effect anymore. But that one's actually about 1,000,000 times weaker than the strong force. So it's 10 to the negative 6. And that particle carrier is the W plus, the W minus, and the Z0 particles. Okay. And then finally, the gravitational force. This is the one that things haven't worked out well with. The gravitational force is about 10 to the negative 38 times weaker than the nuclear force. And that particle is supposed to be the graviton. But no one has, I mean, we have predictions about, just like we did a second ago, with predicting what the gluon should be like. The gluon, by the way, was found to be approximately about that energy level. But the graviton, we haven't found yet. We have various estimates of what we think it should be. If it exists at all, we're still not there. But unlike the gluon, we were able to find something for it. So this actually gets into an area called the quantum chromodynamics, because what we ultimately do is we end up giving these quantum numbers, or giving these particles quantum numbers
that are related to things like color and blue and green and stuff like that. So we end up calling it quantum chromodynamics. And the quantum chromodynamics talks about a pion exchanges carriers of the strong force. So you could actually exchange the pions back and forth with the strong force, and the gluons holding them together, stuff of that sort. So it's really kind of a weird hodgepodge of ideas, antiparticles and particles and all this stuff behaving. So ultimately what we end up getting is several conservation laws to make sense of it. We get Dirac coming along and making his Schrodinger equation that is consistent with relativity. Turns out to be a nightmare. Not only that, it has these negative energies, and he uses that to suggest that basically there's these negative energy states that when a photon hits it, it turns it into electron that pops out in space and leaves a anti-electron as a hole, which is a weird thing, but that's what we call it, a hole, and that is the positron. So that ultimately turns out to be more or less correct, but in doing so, we get all these new factors. So we get baryon number. The baryon number is basically a generalization of the nucleon number, and it's basically defined to be +1 for all nucleons and -1 for all antinucleons. So basically, if you have a neutron or a proton, then that has a baryon number of +1. And that's for neutrons and protons. But an antineutron or an antiproton, which you just indicate with a bar over it, that has a baryon number equal to -1. And then all other types of particles, such as photons, mesons, electrons, leptons, and all those things have B = 0. So these leptons, by the way, are a whole different class of particles too. You'll see the leptons turn out to be actually, if you look at your table on page 931, the leptons turn out to be the electron, the neutrino, the muon, the electron neutrino, the muon neutrino, and the tau neutrino. So for instance, leptons, which I want to say is E minus, I should write it as E with a bar over it. Also your neutron, or your electron neutrino, your anti-electron neutrino, your, I want to say your pion. Let me double check. Yeah, it's not a pion. Sorry, it's a muon. Your muon, your anti-muon. A muon, by the way, is like a really heavy electron. So an electron has a mass of 0.511 MeV per c squared. A muon has a mass of 105.7 MeV per c squared. But other than that, it acts like a electron. So there's also a mu neutrino, and there's an anti mu neutrino, an antineutrino for the mu particle. And then there's also the tau particle and the anti-tau particle. And then, of course, its neutrinos and its antineutrino, like that. So those are all leptons, basically. All of those would have baryon number equal to 0. You can also look that the Higgs boson, which is a fundamental particle, it actually has a baryon number of 0 as well. That's the one that has recently been called in the news. They found it recently. It's been called the God particle. It's basically a particle that a guy by the name of Higgs suggested could explain why everything has mass. And that's sort of a big deal, because basically you need that to make sense of why particles are identical. So, you know, why does the electron and proton, for instance, have the exact same charge, only opposite in sign and stuff like that? So these other gauge bosons is what they're called. The gluon, the photon, the W, the Z, those gauge bosons, by the way, have a spin of integer spin, whereas the fermions we talked about before, which is the electron and other things, they have spin 1/2. So if you see on the table, that's why they're broken up that way. But the gluons, photons, W, Z particles, and the Higgs boson, those are fundamental particles, and they all have boson numbers of 0, as do the mesons. The mesons include the pion, the kaon, the eta, the rho, and numerous others. And then there's the baryons, and the baryons are really the things that partake of the nucleus, and specifically the protons and neutrons. But in addition to that, there's a lambda particle, there's a lambda baryon, there's a sigma baryon, both a sigma plus, or I should say a sigma plus, a sigma minus, and a sigma 0. There's a chi particle. So let me show you what I'm talking about here. For the baryons, some other baryons other than proton and neutron. There is the neutron, there's the proton, but in addition to that, there is the lambda particle. This is the uppercase lambda, a lambda 0. Then of course there's the antiparticle of all these. So there's a N with a bar over it, a P with a bar over it, a lambda 0 with a bar over it. There's a sigma plus, there's a sigma minus, and there's a sigma 0. And then there's, of course, there are antiparticles as well. There's the chi particle, which is basically a long line, short line, long line, and that can have a 0 and its antiparticle, which would be the same thing but with a bar over it. And you can have the chi particle, which is minus, but its antiparticle is the plus. And then there's the omega minus particle, and its antiparticle as well. And there's tons more, but the big thing is these things are kind of crazy, and they have huge masses. Like, for instance, the omega particle has a mass of 1067, excuse me, 1672.5 MeV per c squared. So that the omega particle is huge. The chi particle has 1,322 roughly mega electron volts. The sigma particle has roughly 1,197 mega electron volts per c squared. So there's a lot of different particles. And at the end of the day, you got to know what the rules are that allow a nuclear reaction to occur or not occur. So for instance, there is a decay mode for the sigma plus. If you look on the table, it actually shows you on the table principal decay mode. So if you look at the sigma plus on that column, on that row for sigma plus, you go to the far right and it says you can have a P and a pi. That means a proton and a pi 0, or a neutron and a pi plus. So what that means is this sigma plus particle can decay into a proton plus a pi 0. Well, if that's the case, you should expect the Q value to be positive. So lo and behold, the Q value for this would be the mass of the sigma particle times c squared minus the mass of the proton times c squared minus the mass of the pion times c squared. Well, that's roughly 1,189.4, and these are all MeV per c squared basically, minus 938.57 minus 135.0. So ultimately we get 1,000, positive by the way, 116.1 MeV for the Q value. So definitely that's acceptable. Let's look at the charge, because the charge has got to be conserved too. So in addition to having a Q being positive, that means it's going to occur on its own. It's just decaying. It's not required. This reaction doesn't require some input energy that makes it happen. It's going to happen on its own. But the charge must be conserved. Well, if we look on the left-hand side we got +1 for the charge. And then after we got +1, +0 for the pion, for the proton and the pion. So we got conserved. There's also a baryon number though. So the baryon number beforehand, we got sigma plus, and the sigma plus in fact has a baryon number of +1. But then after we have the proton, which has a baryon number of +1, but the pion, the pi0 particle actually has a baryon number of 0. So we got 1 = 1, so that checks as well. So that's how we know that this is a decay mode for the sigma plus particle. It can decay into a proton plus a pion, a pi minus, that is. The sigma plus also can decay into, according to the table, it can decay into a neutron and a pi plus. So again, you can compute the Q, which in this case would be 1189.4. Again, I'm doing MEVs per c squared, minus 939.6. That's for the electron, minus 139.6. That's for the pi plus, and that gives me a positive 110.2 MeV. So this does naturally occur. It is a decay process as opposed to a reaction. Charge conservation gives me, initially I have a charge of +1, and then finally I have a charge of 0 and +1. So that checks. And then baryon number. Initially I have 1 baryon, a baryon number of +1 for the sigma plus, just like we had before. The neutron, of course, is a constituent of the nucleus and therefore has a +1 baryon number. And the other particle, the pi plus, has a baryon number of 0. So this also checks. So that's one of the rules that you have to use when you're talking about these reactions, whether they're going to happen or not. Another thing that happens in everyday life is there turns out to be some reactions that occur and other reactions that don't occur, and you're always trying to figure out, well, why is that so? Well, it turns out by doing that with all these different reactions, they slowly came up with all these other quantum numbers, one of which is the strangeness quantum number, and other one's the charm quantum number. And under certain circumstances, those things are conserved. And generally speaking, they should always be conserved. But sometimes you have, like the strangeness, for instance, is only conserved when you're dealing with the strong nuclear force. So if you have a reaction that takes place via the weak nuclear force, then strangeness need not be conserved. All of this was ultimately somewhat explained by the idea of the quark model. So it turns out that there's quarks, and the quarks are the up, down, the strange, the charm, the bottom, and the top. And the top quark, for instance, we don't think we'll ever see, because it only has a lifetime of 10 to the negative 25th seconds. But we can now subclassify particles based on their number of protons. So, I mean, excuse me, number of quarks. So for instance, the quarks can be, like I said, up, down, strange, charm, bottom, or top. And some particles only have two quarks. That would be a quark and an antiquark pair. And then other types of particles have three quarks. So for instance, the proton and neutron are made up of 3 quarks. And the pi plus and the pi minus and the k plus, they're all made up of a quark plus an antiquark. So there's a lot of different terminology here. What I want you to do is, when you're doing your homework, look up these answers so you have at least heard these things before, so you'll know which ones have an up quark and a are 2 quarks, basically a quark and an antiquark, and which ones have 3 quarks. And that's pronounced quark, like a QU, because it's actually spelled that way, and it comes from Finnegan's Wake Murray Gell-Mann named it. He's a quite astute scholar in addition to being a physicist. But in doing that, that's how we get the charges that we have of these non-fundamental particles. So these are particles that are not fundamental in that they're made up of other things. The things they're made up of are clearly quarks. Some of the other numbers we run into is the lepton, the electron lepton number, also the muon lepton number, and the tau lepton number. Those are conserved as well. So you got to keep track of all that stuff. But at the end of the day, you're actually capable of deciding what kind of reactions occur and what kind of reactions don't occur based on these conservation laws. I was trying to remember that. That's why I'm a little bit hemming and hawing. I was trying to remember what the names they use for the particles that have an anti-quark and a quark, and then what are the names of the particles that have 3 quarks. If I want to say they're mesons and baryons, but I just can't remember off the top of my head. This is not my area of physics, by the way. Yes, I was right. Mesons consist of a quark and an anti-quark pair, and then the baryons, on the other hand, all consist of 3 quarks. So the baryons are the ones that are made up of 3 quarks, and the mesons are the ones that are made up of a quark and an anti-quark. Beyond that, ultimately what happened was a guy by the name of Steven Weinberg, and check this out. This is Steven Weinberg and his classmate through all of high school. They both went to the same high school, was a guy by the name of Sheldon Glashow. And both of these guys go on to win a Nobel Prize. So you can imagine how tight the level of competition was in high school in New York City with these 2 guys in the same class. But Steven Weinberg's now at the University of Texas. I forget where Glashow is. I've met both of them. Glashow's a punk. I hate him. I shouldn't say that. He's just really rude. He was nice to me, but he was rude to other faculty members, and I didn't like that too much. But Steven Weinberg's, I've communicated with him via email a couple times. Been really, really sweet guy. And then a third guy by the name of Salam in India. They all won the Nobel Prize for basically generating what's now known as the Standard Model. And the Standard Model basically takes and makes the weak force another side, if you will, of the strong force, and combine it with, in fact, the electromagnetic force. So basically our 4 forces, which are the strong nuclear force, the electromagnetic force, the weak force, and the gravitational force, they've condensed down to 2 by creating the Standard Model. And they all 3 did it independently. So they all 3 won a Nobel Prize for that independent work. It's pretty impressive what they pulled off. Actually, I had a question for Professor Weinberg just today, and sent him last night and sent him an email, and I just noticed that he did reply to me. So that's the kind of nice, wonderful person he is. To be honest with you, I've met 4 Nobel laureates so far, and all of them have been really wonderful, except for Sheldon Glashow. Again, it might have just caught him on a bad day, but he was really nice to me. I was introduced to him by one of his friends, who introduced me as his most talented quantum mechanics student, which was really impressive because the next day I ended up failing a test of his. But Glashow was kind of neat. He's just really rude to all the other faculty members at Chapel Hill, so I thought that was kind of a punk thing to do. Anyways, they came up with a Standard Model. You can read about it in section 3210. Basically explains everything, how things are held together. Basically explains everything except for the gravitational force. That's not included in there. To summarize, the Standard Model says that the truly fundamental particles are the leptons, the quarks, and the gauge bosons. Remember, the leptons are the electrons, the muons, and their neutrinos and all that stuff. So the truly fundamental particles are the ones that are made up of nothing. That would be the leptons, the quarks, which are made of nothing, and the gauge bosons. And the gauge bosons, by the way, are the force carriers. So it's the W, the Z, and the gluon, and the Higgs boson. The photons, leptons, W plus, W minus, and Z0 have all been observed in experiments, but only combinations of quarks, baryons, and mesons have been observed in the free state. And it seems like the free quarks and gluons cannot be observed in isolation. One important aspect of theoretical work is the attempt to find a unified basis for the different forces in nature. This was the long-held hope of Einstein, which he was never able to fulfill. So a so-called gauge theory that unifies the weak and electromagnetic interactions was put forward in the 1960s by Steven Weinberg, Sheldon Glashow, and I think it's Abdul Salam. Abdul, I think was his first name, in the electroweak theory. And so they did do this in the electroweak theory. The weak and electromagnetic forces are seen as two different manifestations of a single, more fundamental electroweak interaction. The electroweak theory has had many successes, including the prediction of the W plus and W minus particles as carriers of the weak force, with masses of 80.38 plus or minus 0.02 GeV per c squared. Notice we're talking GeV. These mass carrier, these gauge bosons are really, really heavy. In excellent agreement with the measured values of 80.385 plus or minus 0.015 GeV per c squared. The combination of the electroweak theory plus quantum chromodynamics for the strong interaction is referred to today as the Standard Model. So that really is the crux of where we are or how far we've come. What goes on in physics now is we're trying to, for instance, find a grand unified theory, which is basically one theory that includes all the things. With the success of the electroweak theory, theories are trying to incorporate it and quantum chromodynamics for the strong color force into a so-called grand unified theory. That's what we're looking for. Those are guts, and there's TOE's theories of everything. So they use gut, grand unified theory. TOE, TOE is a theory of everything. All sorts of different models. They use supersymmetry, symmetry breaking, all sorts of junk like that. And all this is actually related, believe it or not, to cosmology, which we'll cover next time. But it's at the end of the day, we're still trying to figure out why are there now at least two separate types of forces, and is there some way we can see them all as the same thing? It's very complicated, but we find that what helps us lead the way is often symmetry. So, if you see, this was a neat thing that happened in physics. So there's this graph that you can make in physics, and it had and this. So this was the graph. And that looks like a problem to me. It's got this wonderful symmetry. If there was just one more dot, say right about there, if there was one more dot right there, it'd be beautifully symmetric. You could say it has a symmetry axis along this line. You could say it has a symmetry axis along this line, along this line, along this line, along this line, all sorts of stuff. So based on that alone, I think it was Murray Gell-Mann and Richard Feynman both suggested there should be a particle right here just from the symmetry of it. And this is sort of the neat thing about physics, is it is about art and beauty and stuff like that. This artistic symmetry was so necessary for our brains. We predicted the existence of a particle. That particle was later found, and that was the omega minus particle. So believe it or not, yeah, there is some sort of artistic weird side to physics where ultimately beauty is important to us, and if something is lacking beauty, we often are very suspicious of it and won't accept it until we can make it prettier or make it more symmetric. And that's where these supersymmetry theories come into play. Emily Noether taught us that whenever you have a conserved quantity, that is due to some symmetry, meaning some way in which you can say rotate this at any angle and it always look the same from every side. That's a particular type of symmetry. That symmetry is ultimately what we call cylindrical symmetry, and that's the reason that angular momentum is conserved. The fact that you can run a clock forward or backwards in time at a quantum mechanical level and get the same thing, that tells you that energy is conserved. So little things like that is what Emily Noether told us. That's Noether. By the way, that is a brilliant mathematician, physicist, and obviously a female. So that's another time where history is sadly forgotten a really wonderful scientist that did happen to be a female, and you just have to wonder why. So
anyways, anybody have any questions on all this hodgepodge of stuff? It sounds confusing, partly because, again, this isn't my field, so I'm not as adept in it. Well, I'm excited about it, but I'm not as adept at explaining it in such a way that my exuberance can help for the complications as well as it can, say, in relativity or Newton's laws. But basically, if you can do those examples, like conceptual example 3211 or example 3212, or any of those examples in chapter 32, you should be able to do all those at least like for a homework type problem, and be able to identify the different quantum numbers that are relevant. If you can do that, you've got more than enough understanding of chapter 32. Really, chapter 32 and 33 are going to be a small part of the final exam. Like I said, maybe one question from 32, one question from 33, and that's about it. So, anyone have any questions? I'm sorry, I don't think I did as good a job as I would have liked to in this material, but in terms of teaching it to you. But I think you got at least a decent taste of it. And I actually personally never had this at all until I took a elementary particle physics course in grad school. You've probably heard of string theory and quantum loop gravity, at least if you've listened to or watched Big Bang Theory. Those are both theories, again, that are trying to make some kind of grand unified theory. In the case of string theory, you sort of say, well, maybe the electron really isn't infinitely small. You know, it doesn't have any physical dimension. Maybe it actually does have physical dimension, but it's in fact a loop, and it's a loop that goes through 11 dimensions of space and time. You know, 4 of which are ours. And in R4, it just looks like a speck or an infinitesimally small dot. But if you were to look in those other dimensions, the other, 6 dimensions, then you would see some actual size to it. And then if you vibrate that string, that loop string one way, it becomes an electron. Another way, it might become a muon, stuff like that. So that's sort of what those things are about. Not easy, by the way, not easy to deal with. You can imagine it's already nasty because you're talking about 11 dimensions. So all your integrals and stuff like that are 11 dimensional, and it's just a nightmare. I had an impromptu course in that, and I've worked through a textbook on it, but it's not trivial. So you're now up to date on at least the very, very small. As of Friday, you'll be up to date on the very, very large, because that's where we talk about cosmology, the Big Bang, all that good stuff. So if there's no questions, I'll let you go. And yes.
I actually have a question.
Yes.
Is material that is going to be on the final?
Yeah, like I said, you have homework assignments. I already put the homeworks up for the rest of the course. They're all up now. Excuse me. You should expect maybe no more than one question from chapter 32, one question from chapter 33. It might be a conceptual, it might be a problem, either one in both cases. So we're going to have, probably one question on the final from chapter 32 that could either be a conceptual question or a problem, or we might have one from 33 that is either conceptual or a problem. That's about the full extent of it. And what you do in your homework is really the more important thing. If you were able to pull off those homeworks, and then you can do the individual examples in the textbook, and I'm leaning towards the easier ones, then you'll be fine.
Okay, thank you.
No problem. Anyone else?
I'm actually just wondering, for the practice test for the final, when do you think you'll have that up?
I think we'll put it up. I'll probably finish it while you guys are doing your lab, and it'll be posted by the end of lab.
Thank you.
No problem. Anybody else?
I can't see my grades for my labs on Canvas. I only see the grade for the first lab, and after that, I don't see anything else.
Yeah, you're not missing it. It's I've only been able to get the first one transferred over from my phone to it. I'm working on the other one today too. So today I've got 2 things going on. I'm trying to make a practice final, and I'm trying to actually make your test as well. And thirdly, I'm trying to get more of those labs crossed over into the lab manual. So we'll have more of those graded Don't worry, I don't stack the errors. So those of you now know what your errors were in lab 1. If lab 2 has the same errors, I'm not going to hit you again for the same thing because you haven't had a chance to grade that. Okay, just make sure you look at your grade and see what was erroneous about your lab. I have one student that actually they didn't do some part of it, so they got essentially a 0. That 0 is not permanent. Actually, I have a couple students I think that happened to. That 0 is not permanent. All you have to do is resubmit it after the suggestions I made, and that'll give you a real grade that I won't count as late or anything. The people that got in the 90s and the 80s, those grades are set, but the rest of the grades are going to be much higher. And I think I'm probably going to drop the lowest lab grade. So, all right. Lots of stuff said there. I'll let you guys go. Hey, let's meet at the other chat room at 12. I sent you all an email with 3 YouTube links. Those 3 YouTube links are what the lab's about today. I think I put them in the right order, but I might have put them in the wrong order. The main thing is that's the lab material we're going to do today. So I want y'all to watch it before you come to class. So let's meet at, instead of 12, let's meet at 12:10. That'll give you enough time to watch those videos. Talk to you later, folks. Have a good day.